Hello students, welcome to the classes. In this session, we will continue with semiconductors. In the previous session, we have seen about intrinsic semiconductors. What are intrinsic semiconductors? Their conductivity is purely because of what? Thermal breakage of covalent bonds. Right. Now in this session, we will see about extrinsic semiconductors. Okay. So let's see about what? Extrinsic semiconductors. Extrinsic semiconductors. Okay. So in intrinsic semiconductors, except silicon, or we call those as pure semiconductors also, because we had only silicon, we did not add any other impurities. Okay, now in case of extrinsic semiconductors, what we will do is, for the pure silicon we will add some impurities. Okay, now let's see how the structure will look like. Okay, now initially we had what? We had, the silicon structure in solid state was like this, right? They used to bond, they used to form what? Covalent bonds with the neighboring atoms, right? Now let's draw the structure. Okay, so this is silicon, now this is silicon, right? Now this is silicon, this is silicon. I am drawing the structure here. Okay, so this was pure silicon. Now in each bond there were 2 electrons, right? And see here, now if one of the bonds break, what happens? These 2 electrons will become free, and here we used to get what? Holes. Now this was the case of what? Intrinsic semiconductors. Now here each silicon shares 4 electrons. Now if I add impurities, okay, what are impurities? Silicon is tetravalent, it means it shares how many electrons? 4 electrons. Now if I add pentavalent atoms, pentavalent, or if I add a trivalent. Pentavalent means having 4 electrons in, having 5 electrons in the outermost shell. Trivalent means having 3 electrons in the outermost shell. Now let's see the first case. Okay, let's add pentavalent. Okay, what happens if I add pentavalent atoms? For example, instead of, if I add arsenic, few arsenic atoms to the pure silicon, okay, one of these silicon atoms will be replaced by arsenic. Now let's replace this. Okay, so let me take out this. Let's see the case. Okay, so what I will do is, one of the silicons I will replace by arsenic, because I am adding few arsenic atoms. Okay, so now one of the silicons is replaced by arsenic. Now see how will be the structure. As I told, arsenic is pentavalent. It means it has 5 electrons in the outermost shell, right? Now what it does is, it shares these 4 electrons. It has whatever the 4 electrons it had, it shares those 4 electrons, but actually it has how many? 5. So what happens? This silicon will give 1 electron, this one will give 1, this will give 1, this will give 1. Actually these 4 electrons belong to arsenic, but where is that one more electron? That one more electron will escape into the conduction band. Okay, this electron will become free. Why? I told you every atom wants to achieve what? Octet configuration. Now this arsenic has already achieved octet configuration. You can see 2, 4, 6, 8. Now the electrons, what actually arsenic had? Arsenic had 5 electrons. Now it is sharing 4 electrons, and it leaves 1 electron. That 1 electron jumps into conduction band. Okay, that 1 electron has jumped into conduction band now. Okay, now because of thermal breakage also, few bonds may break. Let's say this bond has broken. Okay, now I'll get what? 2 holes here, and I get what? 2 electrons here. right? Now see how many free electrons we have here. See, here we have 1, 2, 3 free electrons we have, right? I'll just make them little bigger so that you can see. Okay, there are there are 3 free electrons, but how many holes? We have 2 holes. There are 3 free electrons but 2 holes. It means number of free electrons is more here. But in case of intrinsic semiconductors, number of free electrons was equal to number of holes. Now here you can see number of free electrons is more. Okay, so in case of this, the number of free electrons is more. Free electrons are more here compared to what? Compared to the holes. Now such semiconductors, we call them as N type of semiconductor. We call them as N type of semiconductors. And N type of semiconductors are obtained by what? By adding the impurities which have pentavalencies. The pentavalent impurities. It means having 5 electrons in the outermost shell. Okay, now whatever the impurities I am adding, for example, arsenic is my impurity here. That impurity we call it as dopant. That impurity we call it as what? Dopant. The impurity we are adding to the pure silicon, that impurity we call it as dopant, and this process of adding impurity we call it as doping. Doping means what? Adding the impurities to the pure silicon. That process we call it as doping. The impurities we are adding is called as what? Or they are called as what? Dopants. Now here the dopant is what? Arsenic. And here you can see this arsenic is donating one extra electron to the conduction band, right? It is sharing the 4 electrons and it is donating one extra electron. That is why the pentavalent impurities are also called as donor atoms. They are called as what? Donor atoms, because they are donating one extra free electrons, right? And there are more free electrons compared to holes. Okay, the more, the charge carriers which are more in number are called as majority charge carriers. It means here the free electrons are majority charge carriers. What about holes? Holes are nothing but what? Minority charge carriers, because they are less in number. Right, now this is about what? This is about N-type semiconductors. Okay, now let's see about what? P-type semiconductors or the trivalent impurities. Now let's see what happens if I add trivalent impurities. Okay, I'll just erase this part. Let's take the same silicon structure. Okay, so let's consider the silicon structure here. I will form the covalent bonds here. Now these are forming what? Covalent bonds, and in each bond there are 2 electrons, right? Now what happens if I add a trivalent impurities? Trivalent impurity, for example, let's take example of gallium. Gallium has 3 electrons in the outermost shell, or 3 electrons in the valence shell. That is why it is called as trivalent, tri for 3. Right, now if I add what? Gallium to the pure silicon, one of these atoms will be replaced by what? Let's say gallium I am replacing. Okay, now what happens? Gallium has only 3 electrons, right? It can share only 3. So let's say this gallium shares 3 electrons here, right? Now here there is no electron to share. So it means there is a vacancy, or there is a hole, okay, created by adding what? Gallium. Now because of thermal breakage, if some bonds break, now these free electrons, they'll come out, and the holes are created here. Right. Now here you see how many free electrons we have. We have 2 free electrons. How many holes we have? 1, 2 and 3. There are 3 holes, 2 free electrons. Holes are majority carriers here because they are more in number. Free electrons are minority charge carriers here. Right. Now here, if I mean this, we have a vacancy, an extra vacancy here. So what is meant by vacancy? Absence of electron. So it means it is ready to accept the electrons. Right. Gallium is ready to accept the electrons to achieve octet configuration. That is why these atoms, this gallium we call it as acceptor atom, or the trivalent atoms are called as what? Acceptor atoms, because they are ready to accept one electron to achieve what? Octet configuration. Right. Now such semiconductors are called as what? P-type semiconductors. Such semiconductors are called as P-type semiconductors. So now P-type semiconductors are obtained by what? By doping or by adding trivalent impurities. Right, by doping with trivalent impurities, we get P-type semiconductors. Right, in case of N-type, by doping with what? Pentavalent impurities. Right, now here in case of P-type, holes are majority carriers because they are more in number, and free electrons are minority carriers because they are less in number. Right, now let's see the difference between N-type and P-type semiconductors. Okay, I'll just erase this part. Okay, how we got extrinsic semiconductors? We got extrinsic semiconductors by adding what? By adding impurities. Okay, now before looking into difference between N-type and P-type, we'll also see difference between intrinsic and extrinsic semiconductors. Okay, now let's see the difference between intrinsic and extrinsic semiconductors. Extrinsic semiconductors. Okay, now intrinsic semiconductors, have you added any impurities? No. So here no doping, or I can say no dopants are added. No dopants are added. Right. Now here in case of extrinsic, we are adding pentavalent or trivalent dopants. Right. Pentavalent or trivalent dopants are added. Trivalent dopants are added. Right. Now these are called as pure semiconductors. Pure semiconductors. Right, because we are not adding anything. Right, it's purely made up of silicon. Right, now these are called as doped semiconductors. These are called as doped semiconductors because we are adding the dopants. Right, now here, what about the conductivity here? Conductivity is very low because the charge carriers were less. The charge carriers were obtained only because thermal breakage of what? Covalent bonds. Here charge carriers are obtained because of thermal breakage also, and also because of doping. Right, so here there are more charge carriers. It means the conductivity is more in case of what? Extrinsic. Right, here they have low conductivity. They have low conductivity. Okay, now here they have high conductivity. They have high conductivity. Okay, now what about here? I mean, here the number of holes and number of free electrons, right, they are equal. Right, here the number of holes and number of free electrons was equal. Number of holes is equal to number of free electrons. Right, now in this case, see, in this case, in case of what? N-type, free electrons were more in number. In case of P-type, holes were more in number. It means what? The number of free electrons is not equal to number of holes. Number of free electrons is not equal to number of holes. Right. Now these are the differences between what? Intrinsic and extrinsic semiconductors. Right. Now let's do one thing. Let's see the differences between what? The n-type and p-type semiconductors. Right. I'll just erase this part now. Right. Now let's see the differences between n-type and p-type. And remember, both of them are what? Both of them are extrinsic semiconductors. Right. Now let's see the difference between what? N-type. Okay, n-type and p-type semiconductors. Now the first difference. What's the first difference? Here you are adding which type of dopants? Pentavalent dopants. Right. So here pentavalent dopants are added. Pentavalent dopants are added. What about here? Here trivalent dopants are added. Trivalent dopants are added. Right. Here trivalent dopants are added. Right. And here which are dopants? Are they donor atoms or acceptor atoms? Here they are donating one extra electron. So I can write dopants are donor atoms. Dopants are donor atoms. What about here? Dopants are acceptor atoms because they were ready to accept one electron. Right? Dopants are acceptor atoms. They are acceptor atoms. Okay. Now here, which are the majority charge carriers? It means which are more in number. In case of n-type, free electrons were more in number. Right? Because the dopants are donating extra electrons. Right? So here electrons or free electrons are majority charge carriers. Free electrons are majority charge carriers. Majority charge carriers. Okay. And here the third one here, holes are majority charge carriers. Holes are majority charge carriers. Right. Now what about minority charge carriers here? Here free electrons are majority, means holes are minority. Right. Now holes are minority charge carriers. Holes are minority charge carriers. Now what about here? Free electrons are minority charge carriers. Free electrons are minority charge carriers. Give me an example for this. Example for this is silicon doped with arsenic because it is pentavalent arsenic. Now here example, silicon doped with gallium because gallium is what? Trivalent. Right. Now these are the differences between what? N-type and p-type semiconductors. Right.